Well, I'm so excited to be here talking about these 3 papers that are foundational both to computer graphics and especially to illumination. And before we jump into it, you can kind of think of illumination as trying to understand the light coming from a scene towards a viewer. And we're going to go into a lot more detail on what I mean by that. And now it's very dark. Before we begin, I want to tell you a little bit about who I am, and this now doesn't work. This one doesn't work? Oh, I got it to work. Just hit it. Okay, cool. So I think Zishan mentioned all of these. Thanks, Zishan. I guess the most important one then is I got a cat. She's adorable. Here's a picture of her helping me with the talk. Before we begin, Legal at 2 Sigma asked me to put this in here. I'm going to keep going.
Yeah, I pushed that.
So the point of these papers and illumination in general is trying to generate photorealistic images. And so I think it's helpful to see what type of things we're looking for in the images that we're going to generate. And so one of the simplest is what we call diffuse lighting. And this is the kind of thing you'd see if you shone a light on a matte surface. And so if you have a light that's shining directly onto your surface, it's going to be brightest. And then as you move away from the light, it gets less and less bright until the point when light can't touch it, and then it's dark. The next thing we want to see is what we call specular highlighting. And this gives us the idea that the object is shiny or glossy. And it's giving us this like bright highlight on the sphere. And this is coming from the idea that light's coming in and then bouncing off at kind of a small range of angles. Next thing we want to see is shadows, and we'd really like to see soft shadows. And the idea with shadows is that the point on our surface, for a point on our surface, the line of sight to a light source is blocked. It's obstructed by something else. And with soft shadows, part of the light is obstructed. So if you have like an area like anything above us, maybe part of it is blocked, but not all of it. Next, we want to see reflection and refraction. So we're going to go into more detail about this, so I'm just going to go fast here. We also want to see caustics, which occurs when, in both reflection and refraction, when light is focused on certain points. And so you've definitely seen this if you've ever been like in a pool and looked at the bottom, and you get this brightness here, and you can see it a little bit. It's very dark. And finally, we want to see things like color bleeding, and you definitely can't see this one. If you could see the screens up here, you could see it. But on these spheres here, on the right side of them, they're a little green, and on the left side, they're a little red. And what's happening is light is coming from a light source, bouncing off let's say the green wall, then bouncing onto our sphere, and then bouncing towards our viewer. And we're going to see this a lot, this idea of light bouncing all around a scene and eventually making it to our eye. So try to keep that in mind. And so we're going to look at a few things, and I want to start with a little bit of background so we're kind of have some common ground. And then we're going to look at 3 papers. The first is Continuous Shading of Curved Surfaces by Henry Giroux. And then we're going to look at an improved illumination model for shaded display by Turner-Whitted, and then end with the rendering equation. And so the first thing to start with is the model we're working with. So we have some 3D space, and we have objects that exist in this space and lights that exist in this space. And we have some viewer that exists in the space. So it has a position in the world. And it's looking out somewhere in the scene. So if we consider my eye as the viewer, and I'm looking out in this direction, I've defined the viewer for the sake of graphics. And now what our goal is that we want to generate an image for what the viewer would see. And so the model is kind of like this. So you have your viewer as my eye, and you can imagine my hand as the image that we're trying to generate. And out here is everything that we're trying to render. And so what we want to do is we want to project the objects out here onto this image. And so now it helps to understand what I mean by an object. So we can kind of represent them in one of 2 ways. We can either represent them as a mesh of triangles, and you might have seen this before. If you've played video games, it's probably how it was rendered. And the way this works is that we have vertices that are kind of stuck together, And if you stick enough of them together in the right way, you can build some pretty intricate models. Here I'm showing a dolphin that looks pretty good. The other way you can represent your objects is with functions. And if you do it with functions, your function needs to be able to answer a few things, or you have multiple functions for one object. First is, does a ray intersect with my object? So just true, false. And if it does, where in space does it intersect? And finally, at the point of intersection, what is the normal? And in a moment, I'm going to talk about what I mean by a normal. And so here's a scene of a dolphin swimming in water that was rendered all with functions. And on the right is the code that was used to generate it. And if you get a chance, go look at this. It's incredible. And the code in this window, I don't know if you could see it, is the code for the dolphin. So, that's how you render a dolphin. That's it. So now we have our objects, we have our scene, we have our viewer. Now we want to generate our image. And this is called rendering. We really have two choices on how to do this. And it's going to imply the things we do once the kind of checks we do and the kinds of things we can actually generate. So the first thing we can do is iterate through items. So for each item, for each pixel. And now we want to find out if the object is going to influence this pixel. So here's my eye again. Here's my image. Some point on my hand is a pixel. We have our object here. And what we're doing the check is this pixel between the object and my eye? And in a little bit, I'll tell you what I mean by between. But assuming that there's some line of sight between the pixel and the item, then it's going to influence this pixel, and we're going to draw something here. And by that I mean decide on a color for the pixel based on that object. And the draw something here bit is the whole point of illumination. It's figuring out how we should actually color this pixel. The other way we can do it is by going pixels first. So for each pixel, for each item, and now we have something kind of similar. So we have our eye, we have our pixel, we have our object. We're going to shoot a ray starting at the eye, going through a pixel, and going out into the scene. And we want to see if that ray intersects with our object. And if it does, then we again draw something here. Okay, so that's kind of the basics of rendering. And we're going to see both of these again when we cover the papers that deal with them. So now I want to talk about just a little bit of math. And so the first thing we're going to see is vectors. And if you haven't seen them before, it's a way to encode, in our case, direction. They can also encode magnitude, which is kind of the length of the vector. But for the whole talk, we're dealing with unit vectors, so they all have the same length of 1. The other thing that we're going to see a lot is rays, which is a vector with a starting position. So you can think of our viewer, which is a position and then a direction that it's looking, as a ray. And we're going to see these a lot. The next thing we're going to look at is what's called a normal. And a normal is a vector that's perpendicular to a surface at a particular point. And for a plane, it's going to have the same normal on every point on the plane. But for a sphere or a circle, the normal is different for every point. And for the rest of the talk, just assume that we already have them. And what we're going to use normals for is understanding or modeling how light bounces off of our surface. Okay, so we have the little bit of math we need. So now I want to talk about what I mean by an illumination model. And we represent our model with a function I of two parameters, x and x prime. And what it's measuring is how much light is coming from x prime and going to x. And if we choose x cleverly, like say our eye or the pixel, we get to answer the question of how much light is coming to our eye, and we get to render what we want. Okay, great. These models usually take into account kind of two ideas. So light is going to come to a point from one of two ways. Either x prime is itself a light source, so it's just kind of sending light all around and ideally to x. Or light is going to come from somewhere else, bounce off x prime, and then go to x. And so in the case that light's bouncing around, these models take into account the direction that the light was incoming and then the direction that the light is going to go out to determine how much the intensity of light that's actually going to make it to x prime. And so we're going to look, so here's kind of the simplest one of these models, and it's called Lambert's cosine law. And we use it for diffuse surfaces. And so to understand the intensity of the light that's going to bounce off the surface, we base it off of kind of the cosine of the angle between the light and the normal. And so if the light is directly on top of our surface, so the normal and the light direction are parallel, then we get the highest intensity of light. If instead the light is parallel with our surface, then light's kind of just going to pass over it. And we get no intensity. And in between that, it interpolates based on the cosine of the angle. For the outgoing light, so this is how much light is going, the intensity of light that's going to bounce off. And the amount of light that's going to go in any direction, in the case of Lambert's cosine law, is constant. It's viewer independent. So no matter where you're viewing the surface from, you're going to get the same intensity of light. And we're going to see other functions that deal with this incoming and outgoing light for which that isn't the case, where you're viewing from matters a lot. You can think of mirror reflection as an example of this. Just give me 1 second. There are two types of textures. So you can think of texture as, in the OpenGL sense of you texture a surface. And you can also think of it, oh, sure. Isn't texture involved with this as well? So I'm going to assume what you mean is the texture of the surface and not a texture map. Ignore texture map, the texture of the surface. Yeah, so these are models that are fairly simplistic. So it's assuming that the texture is kind of rough, which is kind of the matte surface that you're getting. We can go into more detail on that in a little bit. So this is kind of the end of the background. Is there any questions on kind of the setup so far?
When you say the angle of light normal, the angle at which the light is hitting normal?
Repeat the question, please.
When you say the angle of light normal, are you talking about the angle at which the light hits the normal?
No, so it's the angle that the light is hitting so it's the angle between the normal and the direction of the light when the light hits the surface. And I'll have a picture of it soon and I'll point it out. Okay, so the first paper we're going to look at is the continuous shading of curved surfaces by Henry Giroux. And besides trying to generate realistic images, he's dealing with some other problems. And it's kind of implied from the number at the top right of this page. It's 1971. Computer science is pretty young, and computer graphics is very young. And so they're trying to solve problems that some of our later papers kind of just take for granted. And so the first problem that we're trying to solve is what's called Mach Banding. And Mach Banding is an optical illusion in which our brain exaggerates the contrast between two shaded regions when the shading abruptly changes. So here we have this dark gray next to a slightly lighter gray. And at the point when they switch over, our brains are highlighting that fact. And the reason this is a problem is that, or one way you could see this as a problem is that early rendering techniques would just set a single color for the whole triangle. It was called flat shading. And so you'd get images that look like this. And okay, good, you could see it well enough. And what they're going for is a cone, like a smooth cone. But what it looks like to me is a wireframe with a canvas wrapped around it. And this is because our brain is keying in on the point when the color switches from one triangle to the next. And so like one of the main focuses of this paper is solving this problem. But Giroux has a second problem. And again, the reason is it's 1971. And so I expect that my laptop is probably about 1,000 times faster than what he had access to. And so he needs some way to deal with this if he wants to render in any reasonable amount of time. And so any paper you read around this time in computer graphics is going to have at least a paragraph that's saying, we've either have put this in hardware, want to put this in hardware, or please somebody put this in hardware. Because otherwise it's just not going to be fast enough. But even once you put this in hardware, it isn't fast enough. And it's because we have an algorithms trouble. Remember that rendering loop I showed earlier? So I've broken it out a little bit further because the pixels in our scene are in a grid, right? Our image is a 2D grid. So we have for each triangle, for each row, for each column in our row, do the thing. But even if we have a modest-sized image and a small number of triangles, we're starting to get about 1 million, we're getting millions of iterations. And if you're just adding numbers on my laptop, remember 1,000 times faster, it's still taking seconds. There's no way you're going to be able to do this and render something where you want to wait for it. And kind of the crux of this problem is that we're doing a lot of work at the inner loop. We can't, the way this is constructed, we need to check everything every time, which isn't great. And so what we want to do is try to remove some of the work either into earlier loops or remove it entirely. And this is kind of the idea of hidden surface removal. And so I'm showing maybe the simplest version of this for which you get real benefit. And so the first thing you do is you take all of our triangles in our 3D space, and we're going to transform them so that they're in what we call screen space. And what I mean by this is that their coordinates, their XY coordinates, are in the same coordinate space as our pixels in our image. And so what this means is that if we have some point on one of our objects, once we do these transforms, let's say at XY coordinate 50-50, and we have a pixel at 50-50, they're on the same line. This is a really nice transformation. And this is how we do that between check that I mentioned earlier. And I unfortunately have absolutely no time to talk about this, but if you're interested, talk to me after about it. And so once we've done that, what we're going to do is for each row, we're going to look at each triangle, and we're going to check if the line segments of our triangle are intersected by our row. And if they're not, then we know that the columns in our row have nothing to do with that triangle. We just throw it out. So this is really good. The other thing, so this works really well. And then we do the draw something here bit, and we have one extra trick, which is once we know where the line segments intersected, we can just iterate over the columns between those two intersections, which is way better than iterating over everything. But we have a problem, which is if we try to evaluate our illumination model, which we're going to look at in just a second, even once we've done all of this, it's still going to be too slow. And so we still need to do something else. And so here's the illumination model that Giroux's working with. And we're summing over our lights and just evaluating Lambert's cosine law. So we're just doing diffuse lighting. And then we're multiplying by a scalar KD, which is kind of the color of our object for the diffuse term. And then finally, we're adding in what we call this I_A is what we call an ambient term. It's to acknowledge the fact that our illumination model is missing a whole lot of stuff. And so instead of things being very dark, we add a little constant extra light to it to spruce it up a little bit. And this is a dirty hack, but it makes a really big difference in your images. But so if we try to evaluate this and do a bunch of dot products at every pixel, it's going to be too slow. And so we still need one more trick. And the trick is linear interpolation. And so once we do these intersections, we're going to evaluate the illumination model at just the vertices of our triangle, so at A, B, and C. And then at the points of intersection in our line segments, so for line segment AC, we're just going to linearly interpolate the color of at those 2 points to our intersection point. And so we get a slightly lighter gray. And we're going to do the same thing on AB. And now for any pixel within that row between those 2 points, we just linearly interpolate again. And so the pixel in the middle over there is even lighter. And so this is really nice for 2 reasons. The first is the whole thing with Mach Banding was because we had these abrupt changes in shading. Well, if you linearly interpolate, you kind of guarantee that you're not going to have that. So, okay, that's great. The other thing is that this is way easier to compute. Once you're moving along this row, it's just adding a single number. And so we can actually evaluate this pretty quickly. So, here's the result of using Giroux shading. So on the left is the flat shading. Again, it looks like a wireframe with a canvas wrapped around. But on the right, I guess you guys see it a little bit. Look at the screens if you want to see a really good version. On the right, it looks like a smooth, solid sphere. So we got exactly what we wanted. But we are missing a lot. We're missing all of the other effects that we were hoping to see. And so the next two papers are going to start to add more of those things. So the next paper we're going to look at is an improved illumination model for shaded display by Turner-Whitted. And if you've taken computer graphics, you've probably implemented a Whitted ray tracer, and that comes out of this paper. And so what Whitted's trying to do is add shadows, reflection, and refraction. And so just so everyone knows what I'm talking about, when I say reflection, I mean mirror reflection. So if you have a mirror and light comes in at it, the outgoing light is going to leave at the same angle that it entered, just reflected about the normal. And then for refraction, if you don't know what it is, you've definitely seen it. If you've ever had a water glass with like a straw in it, and the straw kind of bends once it hits the water, that's refraction. And this diagram is showing it another way. So you have this ray leaving the water, and at the point when it leaves, the angle that it's traveling, it increases. There's a lot of physics that we're just going to assume that we know for how to deal with this. And the amount that it bends is based on the surface, or the medium that the ray is traveling into and out of. And again, we're just going to assume that we know how to do this. It's not really important for the rest. So here's the model that Whitted's using. So the first two terms look exactly the same as the first paper. It's the second two terms that are new. So we have this Ks plus S. Ks is again the color of the object for now for reflection. And S is what he's calling specular reflection, what I'm calling mirror reflection. Then we have Kt times T. T is he's calling transmission. I'm going to call refraction. And on the right is the first figure in the paper. And it's showing the different components that influence the illumination coming off of a surface. And so we have the lights all the way on the right. And then we have these two new terms. We have our reflection and our refraction. And they both depend on the outgoing angle of our viewer in this case. And so what this really looks like is something more like this, where we have our viewer off to the right. And we're trying to see how much light is coming from our surface 1. And to figure that out, we take into account our lights, but we also take into account the reflection and refraction. And so we have the T down there, and we're assuming it's coming from somewhere else. And we have our S, which is coming from a second surface, surface 2. And now to understand how much light is coming from that reflected ray, we need to figure out the light from surface 2. And so to do that, we've taken into account the lights and reflection and refraction. And so to do that, we look at the reflection from surface 2. And then if we hit another object, we'd have to look at the light from the lights and the reflection and the refraction from that one. We get this recursive problem. So to understand the light coming to our viewer, we need to know this whole chain of recursion. And so in order for us to do this, we have to turn to ray tracing. This is the second big thing that this paper is known for. It is this idea. And so the way that it works is that we have our eye, and we have our image, and we have objects out there. And we shoot a ray starting at the eye, going through each pixel, and we're going to see what it intersects out in the scene. And the first thing it intersects with is going to be our x prime for how much light is coming back towards the viewer. And from there, we're going to shoot a bunch of rays to figure out that light. So we're going to shoot one for each light source. And what we're checking is, do we intersect first with a light or with something else? And if we intersect with something else first, it means that the light from that light source is obstructed, and so we're in shadow. So great, we got shadows. We then shoot a ray for reflection, and we know the direction that ray is going to travel because we know the direction it was coming in at. And we just use the mirror reflection rule. We also need to shoot one for refraction. And again, we know the direction it's going to travel. We use the physics that we assume we know. And in both cases, we check if we intersect with an object. And if we do, we now need to compute the illumination from that object coming back to our original surface. And to do that, we do the whole recursive bit. And so our recursive tree kind of looks like the diagram on the right, where we have our initial ray from our viewer, and we hit an object. And now for that object, we shoot off a ray for refraction and one for reflection. And our reflection ray now hits another object, and so we need to shoot off more rays. And this kind of recursive tree leads to one of the most common bugs when implementing a weighted ray tracer, which is you have your viewer here looking this way, and you have a mirror here, and you have a mirror here. And so it bounces off here and goes this way, and then hits this mirror and bounces this way, and then, yeah, you get the idea. Infinite recursion, very sad. The good thing is we can bottom out these recursions and not feel bad about it. Every time that we bounce, the amount of intensity of light that actually makes it back to our viewer is diminished. And so after a few bounces, it's really okay to cut off the recursion. And so here's an image from Whitted's paper, which, okay, good, you can see it enough. From Whitted's paper, and it looks good. You know, we have our highlights, we have refraction, we have reflection, shadows. You know, this is starting to look like a really interesting image. We don't have like a sphere floating in nothingness. You know, this is starting to look interesting. But it doesn't come for free. Whitted included how long it took to render these things, and that image took over an hour to render. You know, we're not playing video games with this. But you know, this does really help us push forward. Between ray tracing and having this idea of this recursion being something that you can actually do, really helps push the field. And so the last paper that we're going to look at is the rendering equation by James Kajiya. And what he does is he introduces an equation that gives us a unified model for all illumination models prior to it. And we're going to see in a little bit that you can see all of the other models as just approximations. And I think Kajiya knew this was going to be an important paper because, I mean, if you look at the paper, it starts with an abstract, and then the first section is the rendering equation. 3 paragraphs in, we have the equation in all its glory. And so here it is. And the first time I looked at this equation, something about it really unsettled me. So like, really look at this equation. I'm not going to tell you what the terms are yet. I think you could find out the unsettling bit without me telling you. So just like take a moment and look. Yeah, so the thing that unsettled me is in this integral. And I haven't even told you what that s that we're integrating over is. And when I do, that'll probably unsettle you. But yeah, this I over here, yeah, that's the I we've been looking at the whole time. And it's that I on the left side of the equation. I don't know about you, but I have never seen a recursive integral before. Yeah, that scared me. I had no idea how to solve this. And so most of Kajiya's paper is spent explaining how to solve this. But first I want to talk about what the terms are and give you an intuition for it. So the first term is the illumination model we've been looking at the whole time. You know, amount of light coming from x prime going to x. We've already seen this. This g term is what we call the geometry term, and it serves 2 purposes. The first is figuring out if light could actually make it from x prime to x. So if x prime is in a different room than x and there's a wall in the way, no light's coming through. And so we just set this to 0, everything else gets zeroed out. It's kind of what you'd expect. If light can travel from x prime to x, then we're going to decrease the intensity of light that actually arrives based on how far away x prime is from x. If x prime is miles away, it's going to contribute less intensity than if it's sitting right next to each other. The next term is what we call the admittance term. And this is to acknowledge that x prime might be a light source. So, you know, it's just sending light to x. So these are kind of the direct terms, the easy bit. So before we talk about the terms in the integral, I just want to give you an intuition for it. You know, we've said that light can come from x prime to x in one of two ways. Either x prime is a light source, so the admittance term we just looked at, or light came from somewhere else, bounced off x prime and went to x. And so that integral is dealing with the bounced off x prime. It came from somewhere else, bounced off x prime, and went to x. And so that s that we're integrating over is every point in the scene. So yeah, also good luck. So our x double prime is some other point in the scene. And we're trying to see how much light is coming from x double prime, bouncing off of x, and going x prime and going to x. And so this first term, this row of x prime, x double prime, is what we call a bidirectional reflectance distribution function, or Brdf. And I'm going to call it Brdf for the rest, I promise. And it's dealing with how much of the intensity of light that came from x double prime and hit x prime actually makes it to x. And so it's dealing with the direction of the incoming light and the direction of the outgoing light. And you should be thinking, I feel like I've heard of this before. We've already seen one of these. The Lambert cosine law is an example of a Brdf. But they get a lot more complicated than Lambert's cosine law. You can have things like mirror reflection, which would be 0 everywhere except where in the same angle as where the light came in from. And you can have all sorts of things in addition. And one of the things people do is that they'll empirically generate these functions. So they'll take an object and actually measure the Brdf. And so this means you can really take into account kind of the texture of the scene. And so this kind of touches on what you were asking earlier. But there's an even further bit that we'll talk about after at the bar. So that's that. And then finally, we have the light actually coming from x double prime and going to x prime, which once we know how much is actually going to get to x, we have everything. And so before I go any further, does the intuition and the terms here make sense? Are there any questions about this? Yeah, what's up? Wait 1 second for a mic. Or, yeah, it's going great.
So the row of x prime, x double prime is like an amount of like 40% of the light or something?
Yeah,
from x double prime to x prime to x?
Yeah, you can think of it as a scalar.
When you refer to the points in the scene, are you talking like, is this 3D space or 2D space?
3D space. That's a good question. Yeah, since the Whitted paper, we're dealing with 3D space. We've stopped projecting things to screen space. That was nice, but gave us other problems. Okay. So now's the bit where we figure out how to solve this. Oh, one more? Sure.
If we were to assume that the object was a perfectly black object which does not reflect any kind of light, I was just wondering if you could just walk us through how this equation would turn out.
Sure. So if we don't cheat and just set the geometry term to 0 because we know that, so let's ignore that case. So
Yeah.
light could get from x prime to x. So we'll just do the normal thing. X prime is definitely not an emitter.
Yeah.
And so now we have this integral to deal with all the other light that's coming through. And so there can be light coming from some other point towards x prime. So that's our object. That's a black hole. And so that's fine. That term is going to have a value. It's this rho term that's going to be 0.
Oh, okay.
So it depends on the incoming light, the outgoing light, and the surface. I should have said that.
Okay.
The x prime being in one of the parameters, kind of is meant to be able to address the fact that it can be different for every surface. So this Brdf can be different for each surface.
Okay. Thank you.
You're welcome. Okay. So now the first thing that Kaguya notes is that you can approximate this function. And don't try to read this. I'm going to walk us through it. So at the very top here, we have I equals g of epsilon plus. And so what he's doing here is he's taking the integral and turning it into a linear operator, a matrix. And then he's doing a little bit of algebra, doing a matrix inversion, and then doing some math that I don't really know to say that you can look at this as an infinite series of terms. And so that's this bit here, the GE plus GM, GE, so on and so forth. And a few nice things come out of this. The first is that it gives us a really nice interpretation of this equation. So you can think of the light coming from x prime going to x as the sum of the light that goes from x prime to x because x prime is a light source, plus the light that comes from x prime that goes to x because light from a light source hit x prime and then went to x, plus the light that bounced off some surface, hit x prime, then went to x, plus the light that hit some surface, hit some other surface, hit x prime, then went to x, and so on and so forth. And so the light that's finally going is the sum of all of these different bounces. And so, at least for me, this was helpful to think about. The other thing that comes out is that we can look at prior models as an approximation in this kind of framework. And so the first one is what he calls a Utah approximation. And Henry Giroux, the guy who wrote the first paper, was out of Utah, out of the University of Utah, which had a big computer graphics group at the time. And so you can represent the model as this really, really small equation. And so you have he deals with light sources, so you get that. And you also get just the single bounce. So light source to our surface to our viewer. And there's one other interesting thing that comes out of here is that you can see why they don't have shadows. If we go back one, in each of those terms with the m in it, there's a g between the m and the admittance term. But here they don't have it. They're not actually doing the check to see if there's anything in the way, and so they don't get shadows. Okay, so that's kind of cool. We also get Whitted's model. So here we have our infinite series of bounces. And in Whitted's model, here we have this m naught, and that's because we're not dealing with all bounces, we're only dealing with mirror reflection and refraction. Okay, so that's pretty nice, but this is not how we're going to actually solve this thing. What we're going to do is try to estimate the integral. So I'm going to bring us back to like first year calculus. Think of solving an integral as trying to figure out the area under a curve. And one of the first ways that you learn how to do this and how to approximate it is with something called Riemann sums. So you take samples of your function at fixed intervals and then calculate the area of the rectangles that those intervals imply and sum them, and that gives you an estimate of your integral. So there are a few problems with this. It doesn't work that great in 3 dimensions. It doesn't work that great if your function is not very smooth. But it's a good intuition. We're taking samples and trying to estimate the full integral from that. So what we're actually going to do is do something called Monte Carlo integration. And it turns out that the math behind this is fairly simple. So I'm just going to go through it kind of briefly. But the intuition is we're taking samples and we're using some kind of basic statistics to try to infer the full integral. And so the math behind it is based on the expected value in statistics. And so we need to know 2 things about it. So if you haven't seen an expected value before, the way that you calculate it is that for the expected value of some variable is the integral of over every value it can take times the probability of that value. Well, the first thing we need to know for Monte Carlo integration is that if you apply a function to that variable, the calculation doesn't change too much. Instead of taking the value times the probability, you take the value applied with the function applied to it times the probability. That's the first thing. The second thing is that we can estimate our expectations. We take samples, and in the case of the function, we apply the function and then take the average. And this gives us an estimate of our integral. And so how we're going to use this is that we have some integral of some function g of x, but we don't know how to integrate it. What we can do is we can multiply by some function p of x and then divide by p of x. And I should note we haven't actually done anything. We've multiplied by 1 effectively. But if we choose our p of x really carefully so that it's a probability distribution function, then we can look at this as an expectation of g of x divided by p of x. And I'm using the first thing that I noted about expectations, where our f of x here is g of x divided by p of x. And this is nice because we know how to estimate this. What we can do is take samples, apply g of x, divide by p of x, and then take the average. And so I want to show a quick example of this. Live demos, let's hope this works. Okay, so what we want to do is find the integral of x squared between -1 and 1. And we're going to pretend like we don't know how to do this. Make it bigger. Is that making it bigger? Yeah. Cool. One more? Good? Yeah. Great. So the integral is 0.666 repeating, but we don't know that. So what we're going to do is we're going to take samples uniformly randomly between -1 and 1. So that's the range that we're integrating over. And we're going to compute the area using the function that I just mentioned. And so it's going to print a figure showing our function, our samples, and also the area. And so here's our first evaluation. We get 0.600, and here are our samples. And so I'm going to do this a few times, so I want you to get a sense of the values coming out. We get 0.64, 0.66, so that one's good. 0.73, 0.60, 0.54. What you should notice is that there's a lot of variance here, and there are two reasons for that. The first is that 100 samples really isn't very many. The second thing, though, is that we're sampling over the whole region uniformly. And there's a whole lot of the region, especially in the middle between -0.5 and 0.5, where the value is pretty small. And at points it's 0. So if you sample and get 0, you don't really find out very much about your function. So you don't find very much about your integral or your area. And so one thing you can do is you can bias your sampling. So what we're going to do next is we're going to sample more frequently between -1 and -0.5 and 0.5 and 1. And so 2/3 of our samples are going to come from those two regions, and only 1/3 is going to come from -0.5 and 5. And so now our p of x is not constant. We're going to have to take that into account. But what this should mean is that we're going to get less variance and better estimates with fewer samples. And we're doing a live demo with randomness, so wish me luck. So our first sample, we get 0.69. Here are our samples. 0.65, 0.62, 0.66. It's a little bit tighter. If we keep hitting this, it probably will show that I'm wrong. But right now it looks good, so I'm going to stop. And so this idea of sampling regions with high value is going to come up again when we apply it to the rendering equation. And it's called importance sampling. And so the way that we're going to apply this to the rendering equation is when we have our x prime, we're going to shoot a ray out into our scene and hope that we intersect something. And when we do, we now have a new point, our x double prime, that we can now evaluate this function. We can take samples. And so we're going to shoot a bunch of rays and start to compute this integral by just taking the average once after we calculate it for each individual point. And so for each sample, what this ends up looking like is we have an initial ray from our eye. It hits x prime. We shoot off into the scene. We hit some other surface, and finally get to the light source. And we propagate the light back. And that's our first sample. And we're going to keep shooting these paths. And the more paths that we shoot, the better our image is going to look, because we can keep, because if we take an infinite number of samples, we'll hit everything and everything will be great. We won't do that, but hopefully we'll shoot enough that we start to get convergence in our images and they start to look good. And so this technique is called path tracing, and it's really powerful. It's how we can render really photorealistic images, because we can start to estimate the full rendering equation. But there is a problem, and it's a problem of variance reduction. It's a problem that we just saw when we were doing it with our really simple example. A lot of points that we're going to sample from and a lot of rays we're going to shoot are going to have either very little contribution or no contribution to our integral. We're either going to shoot off and hit nothing, or we're going to shoot off and maybe hit something that's very dark, maybe our black hole object. And so our goal now is to try to sample so that we hit high value regions that are going to contribute a lot of light to X prime. And one way to do this is to sample knowing something about your Brdf. And so this is an example of a Brdf where the hemisphere bit is our Lambert cosine, and the spike coming out of it is dealing with specular reflection. So this is the thing that gives us our highlights, our shine, things that make our object look shiny. And if we just sampled uniformly randomly, we might not sample that at all. And so we would miss large, important parts of our full estimate, and we'll get bad estimates. And so one thing that we try to do is we're going to try to sample, keeping in mind our Brdf, so that we make sure that we sample along this spike as well as along the whole hemisphere. And a lot of work after the rendering equation was on figuring out how to sample really, how to make our sampling work well, so we can converge faster and take less samples. So before we wrap up, I want to show you an example of path tracing. And this comes from a site called Made by Evan. And he's implemented a path tracer in the web browser using GPUs. It's super impressive. And so this is an image that's had enough samples that it's pretty much converged. And oh man. All right, everyone try to look at the screens. Although actually you might be able to see the effect that I want you to see. So it's probably okay. I'm going to jigger the image around a little bit, and it's going to have to recalculate from 0. And so at first it's going to look really spotty because some of its samples aren't good, it hit low value regions. And then as it takes more and more samples, it's going to be able to get a better and better estimate. So here I'm going to move it around, and okay, good, you can see. And now I'm going to stop moving it, and it's going to slowly move towards something smooth. And if we let it sit for just a little while, it's going to converge to like a smooth image that we expect to see. And so this is path tracing. In 1986, it was a lot slower, but like this is the idea, and it's really nice. Okay. So I guess to wrap up, we looked at 3 papers. The first was continuous shading of curved surfaces, and Giroux was trying to render realistic images given that it was 1971. So first we were trying to get over some smaller humps like Mach Banding. And our illumination model is pretty simple. We just have our ambient term and Lambert's cosine. And the way we were able to get things to go fast enough was to put it in hardware to have some good hidden surface removal and good old linear interpolation. Next, we looked at an improved illumination model for shaded display. And with it adds mirror reflection and refraction, as well as actually checking if things are in shadow. And here we introduce the ray tracer, the weighted ray tracer. And finally, we looked at the rendering equation by James Kajia, which gives us this unified model for illumination models. And we needed Monte Carlo integration and path tracing to actually solve this thing. And so before we go to questions, I want to thank a few people. I want to start with thanking the Papers We Love organizers. I love this meetup. I think it's such a great way to learn about new things and meet great people. Zishan, everyone, thank you so much. I want to thank the people that helped me prepare this talk and make it way better. Leaf and Julia and Kat, thank you so much. And finally, these two guys, Andy and Spike, were my professors when I was studying computer graphics, and really inspired me and influenced the way that I think about learning. You know, I'm sure that you noticed through these papers that there's a lot more in here than just computer science or computer graphics, or whatever that means. You know, we did touch on computer science. We had to build some better algorithms. We touched hardware. You see a lot more of it in graphics. But then we also started looking at things like physics. And I brushed over a lot of it, but there's a lot there. And math, I mean, we looked at geometry, calculus, statistics. And then graphics also touches on a lot of things that you don't normally see in computer science. You know, you have to deal with color theory, human perception, and then even further away, like art and storytelling, and all of these things that come together, you know, really make the field interesting. And it's what I really like about it. And taking the courses with these two really helped introduce me to this and make me see that it's really important. So I really like to thank them for their time and all that they've done. So that's kind of all I have. Are there any questions?
Question?
So I want to thank you for your talk. That was really awesome. I'm pretty familiar with Riemann integrals and Gaussian integrals, but I was never seen Monte Carlo integration before, and you did a great job explaining that. Could you just quickly summarize what the advantage is to using Monte Carlo integration? Because as far as I remember, Riemann integrals can be made as precise as you need to by narrowing the interval, right? So you can get as accurate as you want to an estimation. So what's the advantage of the Monte Carlo approach?
Yeah, so that kind of implies the advantage. So if you just keep making it smaller and smaller and taking more and more samples, yeah, eventually you're going to get, take it to the limit, you take infinite samples, you're going to get the right thing. The problem is that you don't want to take infinite samples, and you don't want to take even, you don't want to even take a lot of samples. And also you know that once you deal with importance sampling, you know that you can kind of just rule out large swaths. Or not really rule out, but you can favor things that you think are going to be better. And so with Riemann integration, it's kind of all or nothing, right? You have to do all of the samples to get your value. Whereas with Monte Carlo integration, you can keep sampling and build a better and better image, or I guess in general, build a better and better estimate of your integral. But at any point, you can stop. Does that make sense? Yeah.
Any other questions? Anyone here?
Just there's a very famous teapot used in rendering all the time called the Utah teapot. Is named the Utah teapot for the exact same reason?
Same one.
All right. The University of Utah. Cool.
Yeah, big computer graphics group.
Told you it was a dumb question.
Oh, it's a totally good question.
Okay, thank you for answering my questions. I have one more, which is more kind of like forward thinking. But as this particular screen demonstrated, sometimes there's an issue with the light source itself.
Yep.
Do any of these models take that into account? And also, can this stuff be extended to multiple light sources?
Oh yeah, all of this deals with multiple light sources. So here we have a sum over light sources. That's how they deal with it in everything 1 and 2. In 3, you're just shooting rays off into the distance. And if you treat your light source as another object that just emits things, then you can have as many as you like.
This might be another dumb question, but can you go back to the Monte Carlo equation? The
Tell me when to stop.
FYI, there are no dumb questions.
No, so I mean, I kind of got lost in the last step over here where you were trying to do an integral and then you just pulled it out and you kind of pulled the p of x out of the integral sign to push it inside. I didn't think integrals work that way, or maybe I was wrong.
Is there a laser pointer anywhere? Let's see if I can.
Yeah,
Oh, hell yeah, there's a laser pointer. Okay.
that was a product
Here,
and you just
here,
pushed it out of the product.
This bit here or down here?
Yeah, when you said expectation was p of x, that was expectation, and then you just pulled it out of the integral side and then multiplied it by.
Sorry, are you talking about up here where we
Yeah.
multiply and then divide? E? Yes. Yeah, so what I'm saying is we're using this trick here, right, where we have this f of x is f of x times p of x, and if we set f of x to be g of x divided by p of x, then if you just plug in this f of x here into this equation, you get this.
Yeah, but that's multiplied by p of x. Okay. Oh, okay. Okay. Sure. Thank you.
Hi. To extend that question,
Sure.
can you give an example of like a typical probability distribution function that you'd use in this case? Like, is it based on the derivative of your surface, or?
Yeah, so, you mean in Monte Carlo integration in general or in rendering?
Both. I
Sure.
guess.
So here, in Monte Carlo integration, the dumbest one you could do is uniformly random, right? Let's say you know nothing about your function except that it goes from x to y. Sample uniformly randomly from x to y. The same thing applies to rendering. The dumbest thing you could do is uniformly randomly. Kind of a silly example is if your surface is a mirror reflector, then you would only want to sample. You can get rid of all of your samples and just sample along from where the ray is coming in. Yeah. And then you can start to build things on top of this where like you do uniformly randomly, but you always sample along that reflecting ray. And then you can build up further on top of that. Does that make sense? Yeah, so your question is, you find discontinuities. So if there are any discontinuities, you always sample along those. But if you just have points that are higher value, then you want to bias your sampling towards that. So like one thing you could do is sample uniformly randomly over the whole hemisphere, and then uniformly randomly within some small patch of the hemisphere. So that would be like a simple version of this. But even that, you also, like the next step after that would be taking into account knowledge about the whole scene. So this is just taking into account your surface and the Brdf. But if you know things about the scene, like you know that there's a whole bunch of bright stuff over there, you want to try to bias your sampling to over there.
Repeat that.
I think you said it overlaps with your Brdf. Yeah, so one thing you could do is just sample your Brdf if you know how to. Often it's really hard to do that. But that still wouldn't be quite good because your Brdf might be set up one way, but all the bright stuff is where your Brdf is small. And so you kind of want to trade off these two things. Come talk to me after. We can go really deep into this.
So I have a question which is not very related to the 3 papers. It's kind of related, but it's about extension. So the thing is that because I'm thinking about like how, like, because you talk about these algorithms, just wondering like what are the possible applications that we can use these algorithms for. And I am thinking about like one possible application we can do is like video games, something like that. So my question is that if we want to apply this kind of algorithms to video games, what do you think is the biggest challenge we are facing?
With the rendering equation?
Just like all different kinds of graphics algorithm?
Yeah, so for video games, it's mostly using, like, I'm going to call Giroux style rendering, or what I guess Giroux would call the Utah approximations, because it's really fast. And then there's a whole bunch of hacks on top of that to make things look nice. The issue with using ray tracing and path tracing is that it's kind of slow. I mean, even the example I showed, I mean, it's not like the fastest thing, but it's pretty good. You know, it took like a few seconds to get a smooth, nice image. Like, you don't want to wait a few seconds for each frame of your video game. And so the main challenge is just making it fast enough that you can render it at 30 frames a second. There's someone behind you.
Oh.
Hey, what's up?
Me? Just like a note on path tracing before I have my question. Disney did a really great video about like Disney's guide to path tracing where they talk about batching rays, which is really cool. You guys should check it out.
Yeah, link it on the meetup afterwards.
Yeah, totally. My question is like with something so definitively named as like the rendering equation,
Yep.
is rendering like solved, or is there other stuff that's being worked on to incorporate whatever the rendering equation doesn't actually encompass?
Yeah, that's a great question. Yeah, it's not perfect. You asked a question about how to deal with textures, and you kind of bake it into the Brdf, but the right way to do it is to acknowledge that, like, you know, there's subsurface information in textures, and so if you were to like look under a microscope at like a diffuse surface, it's really bumpy and rough, and so there are models that try to take this into account where you're actually modeling the fact that your ray hits a little rough spot in the surface and bounces some particular way. That's not really well handled here. And the other thing that's not really well handled is things that have volumetric effects, so like fog. You kind of have to hack it in, where you say that you have your object is like a box of fog, and then your ray hits into the box of fog, and you either bend it or don't bend it, and then it travels a little further and hits some more box of fog, and you know, it's not great. It does work, but like, yeah, there's still more to be done.
I think fog is its own research topic. It actually is.
It is.
There's like a bunch of papers just on fog.
No, it is.
No, Disney actually. Disney and there's a few others. Yeah.
Yeah, there are some things that are like hard, and some of them are like surprising. Fog is one of them. Hair and clothing. Skin, because with skin, like light hits into your skin and it might bounce off, or it might go a little bit into your skin and then bounce around and then come out. And that's called subsurface scattering, and that also is not really great here. So yeah, there's definitely things that this is missing. The rendering equation is a great name, but there's still something to improve on. Yeah.
Oh, it's a minor thing, but back in the infinite series page, in the rendering equation, you said it's math you don't understand, but it's just a geometric series.
Oh, cool.
1 over 1 minus x equals the sum of x to the I.
Sweet, thank you. Yeah, he called it a von Neumann series, which I
Well-
wasn't familiar with and didn't have time to look up. But it's,
Yeah. Yeah, so that's why, not a question, but hopefully not a hateable non-question.
No, thank you.
I was wondering, with things like the fog and dealing with subsurface scattering in the skin, is that a problem with the rendering equation itself, or just our current methods of approaching solutions to it that are tractable?
Yes. Yeah, I mean, there may be ways to treat fog that works really well in the rendering equation, but I don't know enough to know if it's, like, we don't understand enough about fog to represent it well in the framework, or if the framework doesn't work well for the thing we're trying to represent.
Okay. Because, yeah, I was wondering if you could actually treat every object in your scene as like an atom and
Yeah.
model the Brdf of that atom, and then you'd get all the fog effects and things coming out of it. It'd just be really hard to solve in a tractable amount of time.
No, I mean, that's a good point. I think that if you were to do that, then you could just use this and be fine. And by just use this, I mean wait a really long time. But it would work. I think it would work.
One last thing. Also, does color factor into this at all?
Yes.
Okay, because I know that, like, you know, dark surfaces tend to absorb light and lighter ones tend to refract it more.
Yeah, so did I say the bit about sometimes not being correct in order to build intuition? Good. That was this. When I was kind of saying light's bouncing around all over the place, that was a little loose. Yeah, it is bouncing. That's the right part. Yeah, we assume that all of our objects have color, and even that's loose. And our light has color, and by that I mean that it's somewhere in the wavelength spectrum. And as it bounces, the light that actually bounces off is going to change in the spectrum based on what it's bouncing off of. And so that's where you get the color bleeding from. But yeah, going to detail on that was more than I could in the talk. Yeah, a lot of physics.
Thank you, Will.
Thanks, man.
It's awesome. Thank you.